So we're going to take a look at the notes for section 4.3, which is all about what do we do when we have an undamped forcing or forced harmonic oscillator. And so we're going to take a look at what that means. So previously we've looked at what happens when you have a forced harmonic oscillator, and then in section 4.2 we paid close attention to what happens when that's a periodic forcing function. And we discovered that if there's enough damping, that natural portion of the harmonic motion, that stuff that's inherent to the oscillator, we call that the natural portion. And that stuff just kind of dies down, heads to zero, because, you know, if there's enough damping, it would just die down anyways. But it's the external forcing function that plays a role in the long run. So we think of it as the natural and the steady state. Those are the two parts of the harmonic motion that we will see when we're talking about a forced harmonic oscillator. We kind of stayed away from the situations that might arise when there's no damping happening. So we're going to take a special look at what happens when there's no damping. And if you remember, damping in our harmonic oscillator equation was the B term. And so if there's no B term, but we're also going to basically allow for significantly underdamped situations. And that means the B is really, really small. It's basically equal to zero. So this section is going to focus on those two situations. One where there's no damping, and the second, which is kind of a corollary, which is what happens when you have basically zero damping, but not exactly zero. So in general, what does that mean? Well, if you remember, that means your harmonic oscillator equation is going to be something like the second derivative of y with respect to t plus 0 dy dt plus some k times y equals some forcing function. And if this thing is 0, then our homogeneous equation becomes a pretty simple one to solve. It just becomes basically s squared plus k, whatever that happens to be. And so we expect this thing to behave differently if there's no damping. We expect the harmonic oscillator will not have a decaying natural response. That's because B equals 0. So the long run, if you want to call it that, solution for y of t won't just be the external force. So there's more going on here. In other words, we expect the long-term behavior to very, very much depend upon the relationship between whatever's going on here with the harmonic oscillator and whatever's going on here with the forcing function. And so we can say, since the forcing function and the harmonic oscillator both play major roles in the long term or long run behavior, we must consider how they interact. Or relate to each other. So this idea of how similar is that forcing function, if it's periodic, to the periodic nature of our harmonic oscillator. And it turns out that there's a really important relationship here. It turns out if the frequency of the forcing function is just right, And remember, frequency of the forcing function is going to be cycles per second, right? Cycles per unit time. And periodic. And is very close to the natural frequency. Let's see, of the harmonic oscillator. Then we get something really cool, something that we call resonance. So you may understand or have some experience with the concept of resonance, and we're going to try to tie some things together in this section, some kind of everyday examples of resonance. But we're going to remember kind of restrict our examples to the connection with the harmonic oscillator here. So we're going to start by taking a look at what does an undamped forced harmonic oscillator look like if it's a periodic force. And so at the top of the next page, we have an example that we're going to lead off with and say, okay, what happens in a case like this? You'll notice the left-hand side is telling me about the harmonic oscillator, and we can tell pretty clearly that it's undamped, right? So you can tell the harmonic oscillator is undamped. That's because the B is equal to 0, right? But you can tell it's got a spring constant of 2, and if you want to think of it this way, it's got a mass of 1, right? So we can say something about the harmonic oscillator going on over here, but the right-hand side, this forcing function, isn't so well defined. On purpose, we're leaving the forcing function with a parameter in there, the omega value. And those of you who remember your periodic functions, you probably recall that the number sitting in front of the t in there, that's basically going to have an effect on the period of that forcing function. So if you imagine omega is equal to 1 or 2 or 10, we're basically changing how frequently the forcing function is oscillating, between 1 and -1. So this is just a forcing function that oscillates between, the magnitude of which is oscillating between -1. Oh, sorry. I didn't mean to write it with the absolute value. I don't know why I'm doing that. The forcing function is just oscillating between -1 and +1, right? So we have a forcing function that oscillates. Whoops, and I need a less than there. So we have a forcing function that oscillates, and we have an undamped harmonic oscillator. So how would we go about solving this differential equation? Well, we just spent a lot of time in the previous sections learning that the first thing we do is we find the homogeneous solution. The second thing we do is find a particular solution. And then the third thing we do is combine. So we're going to follow those steps to solve the differential equation. And by solving the differential equation, that's going to give us the equation of motion for this harmonic oscillator. Now we're going to leave omega alone as a parameter in there and just kind of see where it leads us. So step 1, like we've done before, we're going to find the homogeneous solution. And so finding the homogeneous solution means that we're going to turn our harmonic oscillator equation, the left-hand side, into our characteristic polynomial. So that'll be s squared. There's no middle term. It's just +2 equals 0. And that pretty simply just leads us to the following, which is s is equal to plus or minus the square root of 2 times I. So we've got imaginary values for our s, which is telling us that we're going to have a phase plane that is rotating around the origin. And because the alpha value here is 0, this thing is just going to rotate around the origin but never increase or decrease in magnitude. So it's basically just orbiting the origin of the phase plane. So what does that mean for coming up with our homogeneous solution? Well, we know that a particular solution for this thing would just be one of these guys here. So I'll just choose the positive value, e to the root 2i t, right? Which we can expand using our buddy Euler's formula. that's going to be cosine of root 2t plus I times the sine of root 2t, right? And so the nice thing about this is we've got two parts of our solution, which we can kind of grab onto and say, well, there's one part right here, and then there's another part right here. Yeah, it's got the I attached to it, but that's just a constant. So really, we have a homogeneous solution that is composed of these two parts, and we just throw constants in front of them. And we have K1. There's no e to the power because there's no alpha value for our S. If you want to think of it in terms of eigenvalue, the eigenvalue is all imaginary. There's no real component. So it's just K1 times cosine root 2t plus K2 times the sine of root 2t. And so what you see here is evidence of our homogeneous solution is telling us that we have motion that oscillates but never decays. So once you set this harmonic oscillator in motion, you'd have motion that just keeps oscillating back and forth, but it's never going to decay. But what happens if we add to that a forcing function? Well, if you have an oscillator kind of going back and forth, it's just never going to decay, and then you give it a push every once in a while, dunk, dunk, and you keep pushing it at just the right time, at just the right frequency, you can make some really interesting things happen. So we're going to take a look at some examples of this and kind of what the physics of it means. But for our purposes, we're going to keep following our process, and we're going to come up with our particular solution. And if you remember, we can guess, and we're going to use our technique from 4.2, that our forcing function is cosine, f of t is cosine, and that means we only care about the real part. And we only care about the real part of our guess, and our guess in this case is going to be our complexified guess, if you want to think of it that way, is some alpha times e to the I omega t, where omega comes from our cosine function right there. So that omega is still sitting in there, right? And so if that's our guess, then that means we have our complexified guess's first derivative, which would just be I omega times alpha times e to the I omega t, because the derivative of the exponent comes down. And then if we take a second derivative, the I omega comes down again. The I and I becomes -1. So this becomes negative omega squared alpha e to the I omega t. So we have our first derivative, our second derivative, and our third derivative. And so we can sub that into our original equation to try to find the value. So that means I'm going to take my equation and say the second derivative of our guess, which is this guy right here, so negative omega squared times alpha times e to the I omega t. Sorry, my omega got lost in the mix there. And there's no middle term, so it's just plus 2 times the original guess, which is alpha e to the I omega t. And the right-hand side is just my cosine function, cosine of omega t, but it's the complexified version of it, so it's just going to be e to the I omega t. And if we play our cards right, which we did, then we know every single term has got an e to the I omega t, and those can cancel out. And that leaves me with negative omega squared times alpha plus 2 alpha equals 1. So a little bit of manipulation. We can factor out the alpha. Remember, we're trying to figure out what's the value of alpha that makes this guess true. So we're going to factor out the alpha and divide, and we wind up with 1 divided by 2 minus omega squared. So it's interesting because my guess in all the problems from 4.2, I would have wound up with something over here that had an I in it. But it's worth noting that there's no I term. There's no imaginary part of this constant. Right? It's just 1 over 2 minus omega squared. The 2 comes from my original differential equation, this guy right here. It's got the 2. And the omega comes from the forcing function's frequency, right? So pretty straightforward. So it seems like all I'd need to do if I want to continue is say, okay, that means that my forcing function, excuse me, my particular solution is going to look like this. It's the alpha, this thing, times omega, alpha, e to the I omega t. Which, of course, we can expand using our old pal Euler. So this becomes 1 over 2 minus omega squared. That's just sitting by itself. There's no imaginary number out there I have to worry about. Times cosine of omega t plus I times sine of omega t. And so remember, we only care about the real part because our forcing function is cosine. So the real part is this thing times my cosine. That's the real part that we care about, because this is the imaginary part over here. So that means that the actual guess, the thing that I would guess, is this guy right here. 1 over 2 minus omega squared times cosine omega t. That's my particular solution. So that means if I do my little combine trick over here, I got to squeeze it in off to the side. I get my overall solution, y of t equals my homogeneous solution from up here, k1 cosine root 2 t plus k2 sine root 2 t plus this term right here, 1 over 2 minus omega squared times cosine of omega t. This is my general solution. This is the general solution for the, and I gave myself room down here, but apparently I ignored it. The general solution for the periodically forced undamped harmonic oscillator is that. And so what we're going to do is we're going to hit the pause button here and give you a little bit of time to think about this, and then we'll talk about this in class on Tuesday. What do you notice about the role of omega? What's important? Well, omega is inside the cosine here, so that's important. But take a look at it here. It's in the denominator. What would happen if omega takes on any particular value? Is there any particular value of omega that might cause problems for this term? What do you think would happen? Well, ponder that. Maybe even try playing around with it in Maple and see what happens. And then we're going to get back together on Tuesday and talk a little bit about this in class.